Hey folks, getting started here in section 11.1. We're going to take a quick look at Taylor polynomials. Now I tend to do this section 11.1 Taylor polynomials when I actually do section 11.3, which is Taylor series. However, folks, if I combine both of those sections like I normally do, if I combine it and try to put it into one video, I'm afraid that that one video will be too long. So this video, I'm just going to focus on the concept of Taylor polynomials, which is in section 11.1. This is exactly what I would do if we were meeting face to face. There are no exercises assigned to do in section 11.1, and that's because our goal is to get to Taylor series, which is section 11.3. So 11.3 Taylor series, it's going to build off of this video. So it might be a good idea to watch the section 11.3 video soon after watching and taking notes on this video while this stuff is still fresh in your head. I mean, if one in section 11.3, we're going to come up with a Taylor series for a function. And if we have the Taylor series, it's going to be easy to write down any approximating polynomial for the function from the Taylor series itself. But what we are going to do here is lay the groundwork for Taylor series to see where this is coming from in section 11.3. So getting on with it, we're going to just call this polynomial approximations of elementary functions. Again, polynomial functions, folks, they're arguably the easiest functions to perform operations on. Operations such as addition, subtraction, multiplication, division, differentiation, and integration. We kind of saw that in section 11.2. Our game right now is to find a polynomial function, and I'm just going to call it P, that approximates another function, and I need to call this other function something, so I'll call it F. So how do we do that? Well, to do this, we're going to begin by choosing a number C that's in the domain of F, at which the function F and the polynomial approximating function P have the exact same value. That is, the polynomial evaluated at C is equal to the function evaluated at C. Note that if we're saying that the polynomial evaluated at C is equal to the function evaluated at C, that just means that the graphs of the polynomial and the function F, they pass through the same point, C f of C. Now, as a matter of convention, we're going to say that the approximating polynomial P is expanded about C or it's centered at C. Does that sound kind of familiar? It should. Now, of course, folks, there are many, many, many polynomials that satisfy the requirement of passing through the point C f of C. For example, if you just consider the function e to the x and say we're looking at the point 0, 1, we're expanding about, the value 0. If you look at the graph of e to the x, there are many, many polynomials that you can draw, that you could graph, that pass through the point 0, 1 on the graph of e to the x. Well, we want to find that polynomial whose graph resembles the graph of f near C f of C. So we want it to look similar to the graph. And one friendly way to do this is simply require the graph of P, the slope of the graph of P, to equal the slope of the graph of f at the point C f of C. So when we start saying we want the slope of the graph of P to equal the slope of the graph of f, that means we want P prime of C to equal f prime of C. Slope of the polynomial equaling the slope of the function. that one extra requirement would yield a linear approximation to the function f, and that's something that we saw in Calculus 1, linear approximations. Now, folks, we should hope to find a polynomial, other than a linear one, that has even better accuracy, that looks more like the graph of f. And to achieve better accuracy, well, let's bring the second derivative into play the game. So that means not only do we want p of c to equal f of c, the polynomial to pass through the point c f of c, p prime of c equaling f prime of c, so that's the slope of the graph of p equals the slope of the graph of f. But let's also require p double prime of c to equal f double prime of c. That would give us a better approximation. It would probably give us a quadratic approximation. The polynomial would be quadratic. So how would we get better and better approximations? Well, to get better and better approximations, we just keep bringing more and more derivatives in to play the game. So let's see where we're at. For any polynomial expansion about an arbitrary value c, it's convenient to write the polynomial in the following form. P sub n of x equals a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared plus a sub 3 times x minus c cubed plus yada 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 plus, I left out a plus in front of the a sub n, sorry, a sub n x minus c to the n. That's the general form of the polynomial. Should look somewhat familiar. So that's our approximating polynomial. We should be able to differentiate that polynomial. So let's look at what repeated differentiation would yield. So we're going to start off by doing the first derivative. So we do the first derivative. Well, we know the derivative of a sub 0. That's a constant. That would be 0. So the derivative of the second term is just a sub 1. The derivative of the third term is just 2a sub 2 times x minus c. Derivative of the fourth term is 3a sub 3 times x minus c squared plus yada 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 plus, and I left out a plus sign again, n times a sub n x minus c to the n minus 1. So that's the first derivative. Differentiate the first derivative to get the second derivative. And the second derivative, well, the derivative of a1, a sub 1 is 0. So the second derivative would just be 2a sub 2 plus 3 times 2a sub 3, x minus c plus yada 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 plus n times n minus 1, a sub n, x minus c to the n minus 2. Remember, it's easy to differentiate polynomials. The third derivative. Well, the third derivative, when we differentiate the second derivative, the derivative of 2a sub 2 is 0. So the third derivative would be 3 times 2a sub 3 plus, yada, 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 plus n times n minus 1 times n minus 2 a sub n, x minus c to the n minus 3. And to kind of get on with it, I'm going to put in some vertical yada yada yadas and jump all the way down to the nth derivative. So if this polynomial were a polynomial of degree 8, n is 8, we would be now looking at the 8th derivative, the nth derivative. So the nth derivative is going to be nothing more than a constant. N times n minus 1 times n minus 2 times n minus 3 times, yada, 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 3 times 2 times 1, a sub n. You still have that a sub n there. So that's what repeated differentiation looks like. I'm starting to see some stuff that looks familiar in there. Remember, if a polynomial of degree n, the nth derivative is a constant. And if you go one more, you do the n plus first derivative. Well, the n plus first derivative would be 0. But I'm seeing some stuff that looks familiar in here. But we want to remember that what we want all of those derivatives to agree with the function f and its derivatives at x equals c. So keeping this in mind and letting x equals c yields, and to see what it yields, folks, I have to head off to the chalkboard. So hopefully you have this written down, because I'm heading off to the chalkboard to see what this yields. All right, folks, this is the last thing right here. I wrote it down on the board. That's the last thing we saw on the slide. And I said, now because we want the function f and its derivatives to equal p and its derivatives at x equals c, I said we get the following, and I wanted to come to the board to do this. So think, we're saying at x equals c. At x equals c. So at x equals c, we're going to evaluate the polynomial at c. So you put c in for the x's. c minus c is 0. That's gone. So everything is gone except a sub 0. And at a sub 0, we're saying that p sub n evaluated at c leaves us with just a sub 0. We want the function to be exactly equal to this polynomial at x equals c. So we want the function evaluated at c to also be a sub 0. Let's evaluate the derivative of the polynomial at c. Well, again, when x is c, all of this stuff will be just 0. 0 plus 0 plus 0. So we're just left with a sub 1. Now remember, we want the derivative of the function evaluated at c to be equal to a sub 1. Let's evaluate the second derivative of our polynomial at c. So when we evaluate the second derivative at c, well, this would be 0, 0, 0, 0, 0. We just have 2 a sub 2. Remember, we want the second derivative evaluated at c to also equal 2 a sub 2. What about the third derivative? Well, we have it right here. Evaluated at c. Looks like, well, that would be 0, so it looks like we're just left with a 3 times 2 a sub 3. And yes, we want the third derivative of our function evaluated at c to equal that same number. So let's do the old vertical yada yada yada. What about the nth derivative evaluated at c? Well, the nth derivative evaluated at c is nothing more than this constant. But notice, let me get my red chalk here. Notice that this right here is nothing more than n factorial. So we have n factorial times a sub n, which we want that to equal the nth derivative of the function evaluated at c. Now I'm getting ready to head back to the slides, and here's what I'm going to do. Here's what we're going to talk about when we head back to the slides. A sub 1, or a sub 0, a sub 1, a sub 2. Notice this is 2 a sub 2. But if I look at that, 2 a sub 2 equals f double prime of c, I can divide both sides of this piece of the equation. I can divide both sides by 2 to solve for a sub 2. Likewise, I can divide both sides of the equation here by 3 times 2. Remember, 3 times 2 is the same thing as 3 times 2 times 1, which is just 3 factorial. So I can divide both sides by 3 factorial to get a sub 3 equals f triple prime of c over 3 factorial. And if I divide both sides here by n factorial, I know what a sub n is. So I'm going to go back to the slides. I'm going to use this knowledge, and I'm going to show you in the slides. I'll write this all down in the slide a little bit more. We're going to take those values for the coefficients, knowing a sub 2 is f double prime of c over 2. We're going to take f double prime of c over 2, and we can substitute it in here for a sub 2. So that's what our next task is when we head back to the slides. So let's get on with it. All right, so hopefully you wrote in your notes what it yields. Hopefully what I did on the chalkboard, you wrote in your notes, because we want f and its derivatives to equal p and its derivatives of x equals c. That fact plus the work we just did on the chalkboard allows us to solve for each of those coefficients, the a sub 0, the a sub 1, a sub 2, a sub 3, etc., a sub n. And when we do that, we have, well, we just had f of c equals a sub 0. We had f prime of c as a sub 1. F double prime of c over 2 factorial. That's what a sub 2 is. F triple prime of c over 3 factorial. That's a sub 3. And, well, the nth derivative evaluated at c divided by n factorial is equal to a sub n. So like I said, some stuff was looking familiar, you know, that factorial notation. But here's the thing. We have solved, or we have determined what the coefficients look like. We have determined what the coefficients actually are. So if we take these coefficients and we substitute it back into the general form of the polynomial, so I'm going to substitute in f of c for a sub 0, f prime of c for a sub 1, f double prime of c over 2 factorial for a sub 2, f triple prime of c over 3 factorial and for a sub 3. The nth derivative evaluated at c over n factorial. I'm going to substitute that in for a sub n. When I do that substitution, it gives us the following. It's a definition. If f has n derivatives at c, then the polynomial, that's the polynomial when I substitute in for all those coefficients. This polynomial has a name. It's called the Nth Taylor Polynomial for function f at c. Now, if we happen to be centered at 0, or we're expanding about 0, so if c equals 0, then we have what is called the Nth Maclaurin Polynomial for f. So a Maclaurin polynomial is just a special Taylor polynomial. Maclaurin is when you're centered at 0. So I'm going to do one example here of coming up with Taylor polynomials. And here it is. We're going to determine the Taylor polynomials of order n equals 0, 1, 2, 3, 4, and 5. And we're going to center it at 0 for the function e to the x. Then we're going to determine the nth Taylor polynomial, p sub n of x, centered at c equals 0 for f of x equals e to the x. Then we're going to evaluate our polynomial approximation at 1 and compare it to f of 1. And I'll probably use the fourth Taylor polynomial, so I'll probably do p sub 4 of 1 and compare it to f of 1. Or maybe I'll do p sub 5. Maybe I'll do p sub 5. So I'm going to head off to the chalkboard and I'm going to do this. And then after we do this on the chalkboard, I'm going to come back here to the slide because I want to look at one more thing to make sure we see the power of what we're doing here. So let's go to the chalkboard and work through this example. And then after the example, we're going to come back and look at one more thing. All right, this example, we're going to do three things. The first thing was determine the Taylor polynomials of order n equals 0, 1, 2, 3, 4, and 5, centered at c equals 0 for the function f of x equals e to the x. Here's the process that we go through to do this. So we want to get the Taylor polynomials of order 0, and then 1, then 2, then 3, then 4, then 5. So here's how I begin. Write down the function. Your function is e to the x. Let's write down the derivative. It's e to the x. Second derivative, e to the x. Third derivative, e to the x. Fourth derivative, yep, e to the x. Fifth derivative, e to the x. And I'm stopping at the fifth derivative because we wanted to go of orders up to 5. If it's set up to 6, I would write down what the sixth derivative is, but they're all e to the x. You want to evaluate the function and all of these derivatives at where it is we are centered. Well, we're centered at c equals 0. So f of 0 is e to the 0, which is 1. F prime of 0 is e to the 0, which is 1. In fact, it's the beautiful thing about e to the x. It is its own derivative. So all of these will have the same value. So let's start listing. I'll show you how to list these polynomials of order 0, 1, 2, 3, 4, 5. So the polynomial of order 0, well, it's just 1. It's not going to do a very good job of approximating. The polynomial of order 1, well, remember the polynomial of order 1, the definition would say that's f of 0 plus f prime of 0 times x minus c. Well, c is 0, so x minus 0 is just x. So we have the polynomial of order 1 is f of 0, which is 1, plus f prime of 0, that's 1 times x. So that's the polynomial of order 2. It's a linear polynomial, linear function. The polynomial of order 2, well, that's f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 over 2 factorial times x minus 0 squared. So that gives us a 1 plus an x plus, this is 1, so x squared over 2 factorial. 2 factorial is just 2. So the polynomial of, well, the next one. This is the last time I'll write this down, but just cranking through purely what the definition would be. F double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed. That gives us a 1 plus x squared over 2 plus x cubed over 3 factorial. And yeah, I know 3 factorial is 6. P sub 4. Like I said, that was the last time I was going to write down purely the stuff from the definition. P sub 4 is f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared. So that's x squared over 2 plus f triple prime of 0 over 3 factorial times x cubed. Well, that's x cubed over 3 factorial plus the fourth derivative evaluated at 0 over 4 factorial times x to the fourth. Well, that's x to the fourth over 4 factorial. And then p sub 5. Well, I think I'm seeing the pattern. That's p sub 5. So in part B, let me erase this. Part B, it just says, determine the Nth Taylor Polynomial. Well, we should see a pattern. We should see a pattern. The Nth Taylor Polynomial. It's nothing more than, look at the pattern for 2, 3, 4, 5. It looks like it would be nothing more than a 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus yada 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 x to the n over n factorial. Which, notice, this is kind of cool. Notice this is the same thing as the series of x to the n over n factorial, where you start at an n value of 0 and you stop at an n value, well, let me just call it n. It's not an infinite series, it's a finite series. You stop at x to the n. So I could represent it as this. But that is the nth. This is the Nth Taylor Polynomial. And then part C, let's see, what did I say here in part C? Do p sub 5 of 1. I think that's what I said, on the slide. So do p sub 5 of 1 and compare to the f of 1. So when I do p sub 5 of 1, well, this is my polynomial, so I'm just putting a 1 in for all the x's. So literally I would have a 1 plus a 1 plus 1 squared over 2 plus 1 cubed over 3 factorial plus 1 to the fourth over 4 factorial plus 1 to the fifth over 5 factorial. And this ends up being, you know what, I'm not going to write down all the digits. It's a 2.716, and the 6 repeats. F of 1. So if we evaluate e to the x at 1, well, we know f of 1 is just e to the first, which is just e, and e is about 2.71828, blah, blah, blah. So the first 5, going up to the degree of 5, you have a 2.716 repeating. F of 1 is actually 2.71828. That's not a bad approximation. Just using that minimum amount of terms to approximate e to the x. But I did say on the slide I wanted to do one more thing before we finish this overview of section 11.1. So I want to go back to the slides, and what I want to do there is I want to look at the graph of e to the x the graph of this polynomial, maybe I'll do this one first, to see what it looks like graphically, what's happening. So let's head back to the slides to finish off this section. All right, folks, after all that work there at the chalkboard, here's the one more thing I thought we would do. I thought we would look at the graph of the function e to the x. So I put that into y sub 1. And in y sub 2, I've put the Taylor polynomial of order 4 for e to the x. And that was, you see it there in y sub 2, 1 plus x squared over 2 plus x cubed over 6, 3 factorial is 6, plus x to the 4th over 24, 4 factorial is 24. And I want to look at the graph of the function and this approximating polynomial. Let's see, on the window, -5 to 5, that looks good. Y-axis 0 to 15, that looks good. So here comes the graph. So first is the graph of e to the x, and the second graph is the graph of the approximating polynomial. So there's e to the x, there's the approximating polynomial. Notice there's an interval here, looks like from about here to right here, where the graph of the polynomial and the graph of the function, I can't tell the difference between the two. They look the same. So how do I get a better approximation? Well, a better approximating polynomial, I would add one more term. So let's come back here and let's see. Let me add on one more term. So the next term, well, the next term would be what? Plus x to the 5th. X to the 5th divided by 5 factorial. See, 5 factorial is 120. So let's see what it looks like when we add just one more term. It looks like the graphs coincide for a little bit larger interval. So as you add on more and more terms, you know, the polynomial approximation, that approximating polynomial, as you add on more and more terms, it starts to match up better and better and better with e to the x. And in fact, you know, we looked at evaluating the fifth Taylor polynomial at 1 and comparing it to f of 1. So let me just do that real quick while I'm here. Oh, you know what? Let me come down here. So let me come here. Remember y1 is e to the x. Y sub 2 is the fifth order Taylor approximating polynomial. So let's evaluate at 1. So we can see, e to the first. That's what the calculator shows me in the table. Let me highlight it. Yeah, that's what e is. But look at the fifth Taylor polynomial. That does a pretty good job of approximating it. I mean, it starts off 2.71. So if we add another term, it would be an even better approximation. So that's it. That's the last thing I wanted to show you about the Taylor polynomial. So that's it for this video. And again, I strongly encourage you, after you've taken good notes on this video, watch this video, I would strongly encourage you to watch the section 11.3 video while this stuff is still fresh. Thanks for watching.